Welcome, you guys. So let's go ahead and do our last section in chapter 6. So this is going to be systems of, instead of equations, systems of inequalities. So a lot of things are the same, like you want to get y by itself and then graph it. The things that are different is that if you have just a less than or just a greater than, it's going to be a dashed line. If it's a less than or equal to or greater than or equal to, then that's going to be a solid line. Okay, so sometimes we'll have a dashed line. That's a hard thing to remember. All right, then another thing too, as far as there's going to be shading involved. So it's not just going to be a line that we're graphing. So that's new. So if you have y is less than or y is less than or equal to, you're going to shade below the graph. And then if you have y is greater than or y is greater than or equal to, then you'll shade above the graph. Okay, so let's go ahead and look at some examples of this. Okay, so we'll start off with one where it's already in y equals mx plus b. So we can see that the y-intercept is going to be 0, -2. So let's go ahead and start with our y-intercept. And then we can see that the slope, the m of the y equals mx plus b, is 3. So 3/1. So because the 3 is positive, we're going to go up. And because the 1 is positive, we're going to go to the right. Okay, so from that dot we made, let's go up 1, 2, 3/1. 1, 2, 3/1. We could also go down 3, left 1, and that would give us the same line. Okay, so we have to look at a few things, okay? So since it is a less than sign, right? That's going to imply that it is going to be dashed. Since there's no less than or equal to, it's just less than. We're going to go ahead and make it a dashed line. Okay, and then since it's y is less than, that means that we're going to be shading below the line. So this way would be up. So I'm not going to shade that way. I'm going to shade this way because that arrow points down. It has nothing to do with left and right. It just has to do with up or down. Okay, now let's talk a little bit about this. Why we're shading, why we're dashing the line really quickly, so that way we understand the purpose of it. So what we're graphing here are all of the solutions to this inequality. So let's say you picked a random point in here. Okay, so let's say we picked that point. Actually, let me make it red so it kind of pops. That's the point 4, 1. Okay, it should work because we shaded it. So if we substitute 4, 1 in, so 1 for the y, and then 4 for the x, we get 12 - 2. And so we get this inequality that says 1 is less than 10. That's true. 1 is less than 10. If we pick a point in the region that we didn't shade, like let's say we pick this point -2, 1. So 1 for the y and -2 for the x. Then we get 1 is less than -8. Well, that's not true. Okay, so that wouldn't be a solution to this inequality. Okay. Now, as far as why we're dashing the line, we're dashing the line to let people know that points on the line are not going to work. If we had made the line solid, then we would say, okay, go ahead and include these. These are solutions. But because we made it dashed, then points on the line should not work. So let's say that we pick this point right here, 1, 1. So if we substitute a 1 in for the y and a 1 in for the x, we end up with 1 is less than 1. Now it's borderline. That's why it's actually on the line, right? But 1 is not less than 1. Okay, so this is false. So that's why we're telling people don't include points that lie on a dashed line. Now we'd only need one little fix to make it true, right? If we had put the or equal to on it, it would be true now 1 is less than or equal to 2. And so we would have had to have made, in that case, by the way, a solid line, right? We said if there's an or equal to underneath it, that you make it a solid line. And that tells people, well, now it is a solution. So hopefully you understand that there's more than just points on the line that are solutions, that the shaded region is the solution. And that if the line is dashed, the points on the line actually are not a solution. Okay, so let's try one where it's not in slope-intercept form, just to kind of remind ourselves how to do that. So we want to isolate the y. So let's go ahead and move the x over. and then we'll divide by a negative. Now remember, dividing by a negative with inequalities means that you have to flip the sign. So we're going to make this a greater than or equal to. Then two negatives are going to make this a positive, and a positive divided by a negative is a negative. So our y-intercept is going to be 0, -3. And then our slope is going to be, since the 3 is positive, it's going to be up. And since the 2 is positive, it's going to be to the right. So we're going to go up 3, right 2, up 3, right 2. Okay, now we can see that the inequality is a greater than or equal to. So that implies that it's going to be a solid line. Okay, so let's go ahead and draw a solid line. Now we just have to figure out which way to shade. So if you go to where the y is isolated, you can see that it says y is greater than or equal to. Well, greater than would mean that we're going to shade above the line. All right, so above would be this way. This is me shading up. So all the points in this region and along the line this time are solutions to the given inequality. So then let's look at some cases that maybe don't follow that same way of doing things, okay? So when there's just an x or just a y. So x equals 3 is a vertical line. It's going to pass through where x equals 3 right there. Okay, and so we can see that since it's a less than or equal to, that implies that this is going to be a solid line. Now this one is a little different than the others in that I don't care about up or down. In this case, less than is going to imply shade to the left. There is no up or down shading this time. There's only left and right. So we're going to shade to the left because these are where the lesser numbers are, okay? If we had shaded to the right, that would be where the greater numbers are. So anything in here will have an x value that's less. Oh, it's -3. Sorry, you guys. I didn't notice that. So let me go in here. None of that's going to change. But let me just make sure I put the line in the correct spot. -3. All it takes is not seeing the pesky negative, huh? Okay. Am I going to be able to drop this? Let's see. Or delete this. Perfect. Okay. All right. So -3. There we go. And then we're going to be shading to the left. So we'll actually get this tiny region right here. Okay. All right. Y equals 2 is actually going to be a horizontal line at y equals 2. So right here is where y equals 2. Now, since it's just a greater than, that implies that this is going to be dashed. So I'm going to go get a dashed line. Okay. And then, oh, that was weird. Disappeared on me. Let me try that again. Y equals 2. There we go. Okay. So this time, what the greater than implies is that we're going to shade above, just like on that first few examples. There we go. So that's all the solutions to these inequalities. So let's up it. Let's make a system of inequalities. So instead of just one, we're going to have 2 or more, okay? All right. So first thing we want to do is we want to take these and get them into, get the y by itself so we can get them in slope-intercept form. All right. Okay, so we're going to move our x over, which will make the x negative, and that's it. I got this one into slope-intercept form. Okay. You know what? I'm going to recopy that in a second in a different color. Okay, so the y-intercept is going to be 0, -3, the last number. And then the slope is going to be -3/1. So this means that we'll actually go down this time and to the right. So we're at 0, -3, and we're going to go down 1, 2, 3 to the right 1. Or we could go up 1, 2, 3 to the left one, which makes more sense because it stays on our graph. All right. So because it's a greater than or equal to, that implies that this is going to be a solid line. All right. And then let me just twist it a little bit if I can. Yeah. Okay. All right. And since it's a y is greater than or equal to, that implies that we're going to shade above. So let me actually just do this. All right, so now let's do the second line. Second line is x plus 2y is less than 4. So we're going to move the x over. And then we'll have to divide by 2 for everybody. So we get y is less than -1/2 x plus 2. So our y-intercept is 0, 2. And our slope is going to be -1/2. So we're going to go down and to the right. Okay, so let's go to 0, 2. We're going to go down 1, right 2, down 1, right 2, or up 1, left 2, up 1, left 2. Now, because the inequality is a less than and not a less than or equal to, that implies that this is going to be dashed. So let's go ahead and make a dashed line. Okay, and then because it is y is less than, that implies that we're going to shade below. So this way for the blue line. Now the solution is actually going to be where you double shaded. Because remember, it has to be a solution to both when it comes to these systems, right? And so those are the only points that are going to be solutions to both. So the actual solution would be in this orange area right there, and any point along this line. Okay. All right. Okay, so let's go ahead and do something called linear programming. Okay. So the purpose behind this is to find the maximum or the minimum value of some objective function given a set of constraints. Okay. So here's our steps. We're going to graph what's called the feasible solutions or the feasible region. We're going to determine the coordinates of the vertices of the feasible region. Then we're going to evaluate the objective function at each vertex. The largest and the smallest of those values are the maximum and minimum values, respectively. So this is leading into a word problem at the end. Sometimes as a business owner or whatever, you might want to maximize something like your profit or minimize something like your expenses, just to give an example for why we're looking for both maxes and mins, okay? So let's take a look at an example that isn't a word problem, and then we'll work our way into one that is, okay? So this one just gives us our objective function and it gives us our constraints. So we're going to graph the constraints. Okay. So let's start with the easier ones first. So I'm going to graph this one right here. So if y is in between 0 and 4, then let me go ahead and graph it in blue. It's going to be a solid line because it's an or equal to. So this is us between 0. That's y equals 0 right there. And then this is where y, let me get the line function. And this is where y equals 4. Okay, and so we know that we would be in between those. Okay, I'm not going to shade right now. I think I'll kind of do it at the end. Okay, so let me go to green and we'll do the x is 0 and x is 7. So x equals 0 is the y-axis, and x equals 7 would be like right here. Okay. So this is x equals 0, Oops, and this is x equals 7. Okay, so now we have to take our inequality. Maybe we'll make that, I don't know, red. So we're going to take the 6x plus 8y is less than or equal to 48 and do what we've been doing. We're going to isolate the y. And then we'll divide by 8 to everybody. So we get y is less than or equal to, this reduces by 2 to negative 3/4. And 48 divided by 8 is 6. So we know that our y-intercept is going to be 0, 6. And then we know that our slope is negative 3/4. So we'll go down 3, right 4. So down 3, right 4, down 3, right 4. And this is also going to be a solid line. Okay. So what would be considered the feasible region? Well, keep in mind that we're shading below that line, right? So that means that the feasible region would be in here. It has to be below the red, but it has to be in between the green and the blue. So the vertices of that region would be the following. It's kind of like a trapezoid. Well, it's not kind of like a trapezoid. It is a trapezoid, right? Okay, so our feasible region is that trapezoid. And what we've done is we've taken every sharp corner, every vertex that exists on it. Okay, this wouldn't be part of it because it wouldn't be within the 2 green lines. Okay, so don't include this vertex. Okay, here's where it ends right there. Okay, so let's go ahead and write down those ordered pairs. So those are going to be the ordered pairs 0, 4, 0, 0. This one is going to be 7, 0. And then there's a couple of ordered pairs that it's kind of hard to tell what they are. So let's go ahead and go in and find the 2 missing points. Okay. So this first point right here, that's where the red line, which is 6x plus 8y equals 48, intersects with the blue line, which is y equals 4. So I'm going to go to the next slide. And let's go ahead and see what we can do with y equals 4 and 6x plus 8y equals 48. So in this particular system of equations, substitution would be the best way to solve it. So we're going to substitute 4 in for the y. So 4 times 8 is 32. So we'll go ahead and subtract 32 from both sides. And then we'll divide by 6. Okay, so we end up with x equals, and we're going to have to reduce. It looks like 2 goes into both of them. So if we reduce by 2, we end up with 8/3. So we know that the y value is 4. So it looks like it's going to be 8/3, 4 for the point where those 2 lines intersect. Okay, so now we want to go in here and get this point. Well, that's where the red line and the green line, x equals 7. That's where they intersect. So we're going to go ahead and substitute again, but this time we're going to substitute in for the x. So 6 times 7 is 42. And then we'll subtract the 42 from both sides. And then we'll just divide by 8. So we get y equals, and I'm going to go ahead and reduce this time. It looks like by 2's again, right? Close in half. So it's going to end up being 3/4. So this would be the ordered pair of 7 to the x, and 3/4 is the y. So 7, 3/4. Oops, wrong way. There we go. Okay, so this is the ordered pair, 7, 3/4. So we have all of the vertices. We've got 1, 2, 3, 4, 5 of them. So what we want to do is we want to take all of those vertices. Now remember how the linear programming works. It says the only values that are going to maximize or minimize it are going to be the vertices. So we're going to substitute those into the objective function. So our objective function for this was this one right here. 17x minus 3y plus 60. So we're going to make a little t-chart, a little table. We'll have our x values, our y values, and what p is evaluated at that point. And I'm just going to put down all of the vertices that we had. So 0, 0 was one of them. This point up here is 0, 4 and 7, 0. 0, 4, 7, 0. And then the 2 points that we just got on this slide right here. One of these is going to maximize our objective function, and one of these is going to minimize. So let's go ahead and substitute them in. So we got 17 times 0 minus 3 times 0 plus 6. Well, the zeros are going to go away there. So we end up with the 60 for that one. 17 times 0 minus 3 times 4 plus 60. So this is going to be negative 12 plus 60. So this one's going to be 48. 17 times 7 minus 3 times 0 plus 60. So this goes away. 17 times 7, I think that's 119. And then plus 60 to that, 179. Sorry, that's pretty ugly. A little bit. There we go. So I'm going to get out my trusty calculator for this one because it's starting to get hard here. All right. I'm trying to do this by hand in this massive problem. So let's see here. 17 times 8/3. Oops, I forgot the 7 and the 17. All right, 17 times 8/3 minus 3 times 4 plus 60. All right, so that is going to be pretty ugly, 93.3 with a bar, or let me put both. We have to have this so we know how big it is. But when we type that in to like my math lab or something, we will want that to be 280 over 2. That's the most exact way of writing it. All right, let me just check that I typed it in right, because I tend to type things in incorrectly. That looks good. Okay, and we're going to do 17 times 7 minus 3 times 3/4 plus 6. All right, so for this one, we end up with 17 times 7 minus 3 times 3/4 plus 60. That one's going to be 176.75. 4, otherwise known as, what was it before it was like 400, right? No, 707 over 4. Box these so you can see how big everything is. Okay. All right. So we're looking for the thing that maximizes it and minimizes it, right? So the maximum is 179. And that's going to happen at 7 commas. The smallest that this is, looks like 48 is the smallest that it is. And that's going to be at 0, 4. So let's go ahead and just, write a nice little summative sentence here. Okay. Profit is maximized. I'll keep in mind, I call them, profit is maximized at 7, 0, and the maximum is 179. Then the profit is minimized at on point, what is it? 0.4. And the minimum is 48. All right. So now what we're going to do is we're going to have to set up those equations. That was given to us, all the equations were. But now on this next example, it's going to be up to us to set them up. So remember, they gave us the objective function and the constraints. Okay, so now let's have us look at a word problem and go in and find them for ourselves. So I have an extra step. Okay. Okay, so let's take our time. Baking a tray of corn muffins takes 4 cups of milk and 3 cups of wheat flour. A tray of bran muffins takes 2 cups of milk and 3 cups of wheat flour. A baker has 16 cups of milk and 15 cups of wheat flour. He makes $3 profit per tray of corn muffins and $2 profit per tray of bran muffins. How many trays of each type of muffin should be made in order for the baker to maximize his profit? Okay, so the first thing that I'm looking at, or I want to write down, is the objective function, the thing that we want to maximize or minimize. So the objective function is the profit one. So we're going to call it P, right? All right, now we think about how this person makes profit. They're going to make $3 for every tray of corn muffins, plus they're going to make $2 for every tray of bran muffins. So basically what I'm saying here is that we're going to let C equal the number of trays of corn muffins. Oops. And then we're going to let B equal the number of trays of bran muffins. All right. Now let's go in and get our constraints or feasible region, right? Okay. All right, so some things that we know. Well, we know that the number of trays of corn muffins can't be negative. So we know that the corn muffins has to be greater than or equal to 0. The same thing is true about the bran muffins, right? You can't have negative amount of bran muffins. So that also has to be greater than or equal to 0. All right. Now let's go in and get the kind of 2 more complicated equations from this, okay? Okay. So you'll notice that they talked about how many cups of milk and wheat flour each one will take. So it says right here that there's 4 cups of milk for the corn muffins. So I'm going to do 4. And then there are, where is it? Oh, right here, 2 cups of milk. I should probably be using this. So let me do this. 4 cups of milk versus 2 cups of milk, right? okay, for the wheat flour. I mean, for the, I'm sorry, for the bran muffins, right? Okay, so to recap, the corn muffins will take 4 cups of milk and the bran muffins will take 2. So let me go back in here and type. Now let me type in it again. Oops, sorry guys, my computer's so slow right now. There we go. Okay, let's see, how can I select this? Oh boy, darn, let me see. Sorry, this program that I have makes it really hard to select stuff. There we go, okay. All right, but now unfortunately that's off the screen, but I'm just gonna roll with it, okay? So for the corn muffins, it was 4 for the milk. For the bran muffins, it was 2 for the milk, okay? Now remember, we only have, if we go back and we look at the problem, go back and look at it. Boy, sorry guys, my computer is lagging. Makes it hard to drag stuff since it's so delayed. I'll get there eventually. Okay. There we go. I'm just gonna erase these lines here. I'm gonna get it to line up because it's too delayed. Okay. All right. So we know that we have 16 cups of milk total, and I'm not even going to try to type this anymore. So this has to be less than or equal to 16. So this is an equation involving all of the milk, right? So for the corn muffins, it's 4 cups of milk. For the bran muffins, it's 2 cups of milk. And we know there's 16 cups of milk total. All right, let's read the next part. So the next part is that there's 15 cups of wheat flour total, okay? And we know that the corn muffins take 3. So we're going to have 3C plus, there we go. And then it looks like 3 cups of wheat flour for the bran muffins also. And this has to be less than or equal to 15 because we only have 15 cups of wheat flour total. All right, you guys. So those are all of our constraints that we're going to get from this. Okay, so it doesn't matter what you let be your x-axis or what you let be your y-axis. So just pick one of them. So let's say that I let the x-axis be corn and the y-axis be bran. Okay. The only reason I thought to do that is because usually we have the x here and the y here. And so it would be simpler to compare it to how we normally solve. Okay. So here we go, you guys. Let's go ahead and graph the feasible region. So we're going to graph each of these lines individually. Let me get my line function out. Now they're all are equal to, so I'm going to pick my solid line. I'm not going to have any dashed lines. All right, C is greater than or equal to 0. All right, so if C is greater than or equal to 0, that means here's where C equals 0. We're going to be above that. All right, then let me graph where B is greater than or equal to 0. So here's where B equals 0. Oops, not on the right thing here. Take 2. There we go. And we're going to be greater than that. So we're going to be to the right. So what we know so far is we're in quadrant 1. We have to be greater than the red line, so above it. And we have to be greater than the blue line, so to the right of it. So we are in quadrant 1 so far. Now let's take the other 2 equations that we have, okay? So we're going to take 4C plus 2B is less than or equal to 16. And 3C plus 3B is less than or equal to 15. And we're going to go ahead and isolate the y's, get them into slope-intercept form. So I'm going to move the 4C over. And then I'm going to go ahead and divide by 2 there, everybody. So the y-intercept for this equation is going to be 0, 8. Okay, there we go. Oops, and of course that is not on 6, 7, 8. Now it's on the screen, you guys. There we go. Okay. And then the slope is going to be this -2. So -2/1. So since it's a -2, we're actually going to go down and to the right. So I'm going to go down to right 1, down 1, 2, right 1, down 2, right 1, down 2, right 1. And that's going to be our line that has to do with the milk, right? Oh, you can tell I made my graph on this. Let me just go like that. Make it. Let me do this. And I'm gonna make it a little bit bigger than I. So right here. So this must be 8 right here. We'll just say 6, 7. Okay. All right. Now we're going to be below that line, right? The reason we're going to be below that line is because it says B is less than or equal to. Okay, so we're below that line. We got to keep that in mind. Now let's go do the other one. So we will move the 3C over. And then we're going to have to divide 3. So our y-intercept this time is going to be 0, 5. And then our slope is going to be -1/1. So again, it looks like we're moving down and to the right. So we're going to go ahead and go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, etc. And we'll go ahead and graph that line. Now we actually got lucky here as far as finding where they intersect because we drew such a perfect graph. But I'll show you how to find it in case you don't have a perfect graph, okay? So the feasible region is going to be, now this is also a less than, right? So it's below that one too. So we said we're in quadrant 1 because we have to be greater than 0 for both the bran muffins and the corn muffins, but we're below both lines. This must be our feasible region then. Okay, that's below both lines. If I shade something like this, that's not below both lines. That's only below the blue line. Okay, so let's get all the vertices for the feasible region. We got 0, 0. We've got 0, 5. We've got 4, 0. And we've got 3, 2. So those are all the vertices that we want to substitute into our objective function up here. P equals 3C plus 2B. Okay, so we have corn, the bran, and our profit. Okay, I remember 0, 0. And I think I remember 4, 0. 4, 0, and 0, 5. And was it 3, 2? Yeah, 3, 2 for the other one. So we're going to substitute these n to the profit function. So 3 times 0 plus 2 times 0 is just 0. And we're looking for the maximum, so I don't think that's going to be the winner here. Okay, so now I'm going to substitute a 4 in for the C. So 3 times 4 and a 0 in for the B. Well, that's just going to be 12 in the box, so I see them. I'm going to substitute a 0 in for the first one, 5 in, that goes away, so just 10. And I'm going to substitute a 3 in and a 2 in, which gives me 9 plus 4, which gives me 13. Okay, so it looks like the point that will maximize is 3, 2, right? That's going to give us the maximum profit. Okay. All right. So let's go ahead and first of all, make sure that we've answered the question. And then How many trays of each type of muffin should a baker make to maximize his profit? Okay. So the 3 was the corn muffins, right? So he's going to need 3 trays of the corn muffins. And 2 trays of the bran muffins will maximize, get this guy out of there, will maximize profit. All right. There's, I'm missing an F there on the, oh, it doesn't want to, gosh, it's so hard to do things on here. Well, you know what? Here's where I'm at. I'm going to go ahead and just write in the F. Good. There we go. 3 trays of the corn muffins and 2 trays of the bran muffin will maximize the profit. All right, so you have an example of a linear programming problem here. Now let's talk about if we didn't have such a pretty graph and we were like trying to find where this point of intersection is, okay? That's going to be where the blue and the green line meet. And this is going to happen on your homework, which is why I wanted to show you this. So if I want to find that point of intersection, okay, so let's just do a slide here. Find the point of intersection of the green and blue lines. This is going to happen. I just want to make sure that you guys are prepared for it. And I didn't do all the easy cases on the homework, okay? All right, so let's go write down those 2 equations. So 4c plus 2b equals 16. 4c plus 2b equals 16. And then the green one was 3c plus 3b equals 15. So then for that, we're going to have to try and use elimination to make something cancel. So I'm thinking about turning these both into 6s. So I'll multiply by a 3 to make that one a 6, which means I have to multiply by a -2 to make that one a -6. So here are the resulting equations here. We've got 12c plus 6b equals 48. -6c minus 6b equals -30. 6c equals 18. Divide by 6. You got c equals 3. Now take c equals 3 and plug it into your favorite equation. Doesn't matter. Let's say we plug it into that one. 3 times 3 plus 3 equals 15. 9 plus 3 equals 15. 9. 3 equals 6. 6 divided by 3 is 2. So you end up with that ordered pair of 3, 2. Okay, sometimes you just are making like a sketch of a graph and you don't have this perfect graph paper and stuff. And you're not sure where they intersect, and you'll need to use that skill right there. Okay, so look at which 2 lines intersected there, the blue and the green, not set them equal to each other. Use them as a system of equations, right? Like we've been doing in chapter 6 so far. Solve that system and grab where those 2 intersect. All right, you guys, thanks for joining me and good luck on the homework.